Today I will do the 7.33 and then the or rest of 7.3 and then 7.4 and then the 7.5. Okay, basically now we will study the under this new hypothesis. So we assume the old hypothesis and now we just assume that this mg is actually in the fixed orthogonal group and the mu g is one, and then it acts on some convex domain in the subspace, actually inside the Sn, um, as well as acting on Si0 infinity, and these of course maps to the k times k double prime on the pi k, and n acts on the subspace fixing every point of S n minus I0. So this is what we can get under the hypothesis like this. So under this hypothesis, we'll work on that. So later on, of course, I will show that these hypotheses are satisfied. Okay, so under this hypothesis, you see n will have this form where C1b and C2b are zero, and of course for these other elements also as S1, S0, S2, 0, and C1, C2, these are zero. So then we recall the projection again, and the gamma has in this section here and acts on properly convex set, and then k equal to this strict join. And k correspond to this point here. Okay. Right. So this should be -2. Sorry, -2. So we also recall this step, this LF7, which is just A7 minus these values like these. Okay, and they satisfy this property from the 7.340, and so so LF7 will so SG will now have every G will be of this form. So this LF7 is how it differing from the sort of the orthogonal times the nilpotent times some scalar. Okay, so nilpotent will be of this form here, and so also we assume that mu is one, and so then we define lambda k to be this number. So k is the one we apply. So this corresponds to this, which is the join here with the to obtain the k, and lambda k double prime to be the maximal norm of the eigenvalue corresponding to SG, and we define this lambda gamma e plus to be the subset, so that this largest norm of these eigenvalue occurred at the vertex k. So lambda 1g is actually lambda kg, and all the other eigenvalue corresponding in occurring at lambda triple prime is strictly less than this number here. And so under this condition, we can show that this lambda k is A1g and A5g and lambda g. So these are all equal. Okay, so mu g was actually some ratio between AG and then A9g and so on. So this is A9g, so you can verify this with that. The lambda transverse maximal eigenvalue is lambda VE in this case. And the lambda 2 second largest norm is equal to this lambda k double prime, so that's the maximal norm of eigenvalue in SG. And so this is not a group, but semi-group, and so this condition lambda LF7 is larger than 0 is called the non-negative translation condition. And we define mu7g to be LF7 divided by this number. So this is like lambda 1 divided by lambda 2. So so it's kind of a ratio between the eigenvalue at k double prime and the k. Okay, so we are looking really on the k double prime join this vertex k. So this condition will have become less than C0 is for some uniform constant C0. So that is the uniform positive translation condition. So this condition means that we don't translate in negative direction too much for this when this is bounded. Okay, so it's positive. So this condition LF7 is bigger than equal to 0 is necessary condition, so it acts on properly convex domain. Okay, so you need this so that the this group acts properly on a properly convex domain. So because if it's negative, then we have this k prime in k0, and then we can so take this mu k. So that this is the hemisphere corresponding to k prime intersect with u, and this is a ellipsoid, and so then if you so because of this, if this number goes to minus infinity, then uh, this will mean that the translation you will map to this, and then by some this corner system, you see that this hemisphere gets ellipsoid becomes a bigger and bigger hemisphere because it's translated downward. So you have this. So ellipsoid looks like a paraboloid in the positive direction. So if you keep pushing it down, then you get a hemisphere. Okay. So that's what at least you need this, and then you define VZ from the matrix equation. So VG is actually sort of you can since 7352, if you go to 7352, so you write it like this. So VG, so every element look like this. So you can define this VG using this equation, and right. Right. So you define these, and then the so gamma m is any sequence, so that this ratio at the vertex k, and then this k double prime go to infinity. So it's just pushing everything to this vertex k. So if you have any such sequence, then you can replace by some other sequence, gm inverse gamma m in gm, so that these these the corresponding vector and lambda star gm is these are both bounded. Okay, so so you choose these gm so that it acts in a bounded manner in k, but you kind of make this vector direction to be bounded. So in the transverse ellipsoid direction, you want it bounded, and in GM to be the also bounded also. But of course, this may not be bounded. Okay, so that's and of course this still these eigenvalue will still go to have the same as before, because this is bounded. Okay, but we want to normalize this part. Okay, so make it bounded here. So that's just some sort of a compact, because there's some fundamental compact domain, you can do this. Okay, so I don't want to really prove that. So basically that, and then so the next lemma is that um, so if you assume these two hypotheses, and then U is convex domain, HK is a hemisphere mapping to, then the interior is not an open domain which contains this here. That's because if you have some at this vertex case some intersection, then you can push this to be bounded and become infinite in here, and then these uh, these so everything is bounded except these ratios. Okay, so then you can show by inverse that um, these actually become a join. Okay, so in that case, only possibility is that there is actually a join. These T orb has to be tilde has to become a join. Okay, so that's the because these are all bounded, and then the thing is that so if this becomes a join, then you can show it's virtually reducible. So this is contradicting the premise. So you assume that it's strongly irreducible. Okay, so the quasi join is that if you have this orbifold with NP NCRN and then the X1 neighborhood, and suppose it satisfy these hypotheses, is two hypotheses, and it satisfy the transverse weak middle eigenvalue condition, and this X one here, and then these are all zero. Maybe these are redundant, but anyway, so and then it normalizes. Then the uniform passive translation condition is equivalent to properly convex neighborhood, whose closures meet this sphere at K at only BE, and this is equivalent to being a quasi joint, and it's zero if and only it becomes a joint. This U is joined, and then it's a quasi joint, and then uh, the U is radially foliated by segment, and this boundary intersect or tilde is strictly convex with limit points here, and this closure U prime intersect with boundary of A is only this part. So part A is the A is the so A boundary A is a sphere containing the sphere at infinity and the K double prime and B. Okay. So then that's the only. So this gives you the when you have a quasi joint N. Okay. So basically the proof is a bit long, and I uh, right. So the basic idea is that you cannot really Uh, so basically we have to assume that if this is a quasi-joint, of course, to show is quasi-joint, and so we have to show that this neighborhood really, convex neighborhood really exists, and the point is that under these conditions, so you just have to look at how the acts on the rays from the origin, and then this uniform condition will tell you that everything will converge either in the in the small vertex side it will or go to point vertex, but in the other direction it will converge to some K double prime join with VE and this kind of thing. So these are just estimating with this kind of thing, and and then, of course, here you using some sort of coordinate to understand these kind of thing, affine coordinate to understand these things. And so how the Aleph must go to infinity and that kind of thing to show these are well defined to get a properly convex domain. Okay, so those are the proofs here. And the final, in this definition, we want to study strictly joined RPN, and is now called the strictly joined N, and so on. Okay, and then the quasi joined will be the cases. Okay, in these cases. Okay. Uh, so so here I show that strictly joined cases do not occur actually. So now we go to proving that if nk is discrete, then we want to prove our main theorem that these ends are quasi-joint. And so here, if you look at this is end orbifold, and then you want to so L is a fiber. Let's say the N will act on this fiber, and then you have quotient like this. Okay, and so of course this is semi-simple action NK is because this is a co-compact and action, right, of the orbifold. So so then the so for each L, you look at how N acts. Okay, so these are compact, and then so this is really some compact orbifold sitting over a compact orbifold with different dimension. So N L minus L mod N is actually some compact orbifold as well. Okay, so if you look at this, then they because this N actually fixes every point. These transfers and the minimal and largest one are all one. So the eigenvalue is one. Okay. So then so then L is actually complete affine space, and these have some unipotent group action. There's some unipotent, virtually unipotent group action. So so then you can show that this is actually a horosphere. So if you have a unipotent action that on a complete affine transverse direction, then it's actually unipotent. That's what we proved in chapter three. So so we have this kind of situation where there's a horrible and then the nx here, and then the everything else is according to. So these hypotheses it will hold. Okay. So so therefore we have this nice situation, and then we have to show the hypothesis 7 3.15 also holds, and then we can show that it has to be quasi-joint. Okay, and then of course then I have to also show mu z is 0. Mu z is always 1 by 7.37. So 7.37 was what? Uh, so in this discrete case, mu z is 1. Okay. Yeah. So so we have this case, and right. Sorry. What am I doing? Right. So right. So this is because this is a group going to here is actually finite group, because so when we are normalizing some discrete group here, so by some orthogonal group. So in that case, the normalizing group has to be finite. So if you have a finite order that group, then these will force it to be usually to be 1. Okay. Right. So I don't want to get into it too much. Okay. And then I want to do the non-discrete case. Okay. Okay. So I will do the non-discrete case after 5 minutes break. Yeah. Okay. So.